So in the previous video we talked about two scenarios in which we might need to calculate the moment of inertia. The first is if shape doesn't matter. And largely this is a statement of it doesn't matter what the shape is of the objects it's rotating because the size of the object is much smaller than the orbital distance. So if there's sort of two distances that we're interested in comparing. One is, well, what's the distance from the axis to the object? We're going to label that perpendicular distance. So this little symbol here we're using is r perpendicular. So that's the distance from the axis to the object. And when that distance is much larger than the distance across the object itself, then effectively the shape doesn't matter, and then we can treat the object as a point particle. To calculate the moment of inertia for a point particle, what we want to do is we want to take the mass of the particle times that perpendicular distance squared. So just looking at this equation then, what it tells us is that the units of moment of inertia are going to have units of mass times units of distance squared. So the SI units for moment of inertia are going to be kilogram meters squared. Now what if we change this? So instead of a situation like we were looking at before, what if we've got something hanging down from a string, it's rotating around in a horizontal circle? The thing that we need to pay attention to here is, well, the length of the string is not the perpendicular distance from the object to the axis of rotation. So there may be additional distances that you're given in a problem that aren't the perpendicular distance that you need. You'll need to go ahead and calculate out what that perpendicular distance is that you can plug in to calculate the moment of inertia for your object. The other detail, of course, is that the closer this object comes in towards the axis of rotation, the less appropriate it is to simply treat it as a point particle. Well, what if there are multiple particles? So let's say that I've got some fixed rod that's bent down at angles, and so I've got a mass over here and a mass over there, and I'm going to treat these rods as massless for the moment. And so I've got this structure that can rotate around, and so now I have multiple particles. Well, the nice thing is that the moment of inertia acts like mass in the sense that all you want to do is add up the moment of inertia of your individual pieces. So if I asked you what was the total mass of the system, you'd say, oh, it's m1 plus m2. And so if we want to know what the total moment of inertia is of a system, it's just the moment of inertia of mass 1 plus the moment of inertia of mass 2. So the nice thing about moment of inertia is when you have multiple pieces, you just add those pieces together.